Okay, and for the final talk of this session, we have Wojciech Štěpančík, who's going to, or was going to talk about towards formalization of Wärn's zigzag construction, but now it is just a formalization of Wärn's zigzag construction. Where's David? Should be in there somewhere. Anyway, take it.
Thank you. Good morning, everyone. As Tom pointed out, the talk is now titled Formalization of Wärn zigzag construction, since the formalization was very recently finished, so there's no reason to get defensive with the two words in the title. And I'll give a broad strokes overview of my path for this formalization of this construction of path spaces of pushouts. I'll start by giving some motivation, talk about what even this construction is, why we care, and give a technical setting of the work. Then I'll give an overview of the zigzag construction itself so that we are all on the same page and know what we're formalizing or what I formalized. And then I'll move on to what I would consider my main contribution, which is formalizing and filling in the details of the proof that the construction actually satisfies the universal property that we expect it to satisfy. So step number one, recall what a pushout even is, right? So we fix this span, F and G, as in the title of the slide, and then we can talk about the structure of cocoons on a specific type, which here means the triple I, J, and H, where I, J are maps and H is the homotopy filling the square. And we say that this cocoon is a pushout if we take any other cocoon on another type, and then that induces a unique function of the vertices such that the red cocoon factorizes through the blue cocoon, which means that we get these two triangles and a higher coherence, which involves all the four surfaces that we see on the picture. Alternatively, we say that the cocoon is a pushout if the function that takes a map out of X to any other type and extends the blue cocoon to a new cocoon is an equivalence. That's the way that it's used in the library that I'm using. And one notational remark, although the cocoon structure is the thing that we say is a pushout, we also often refer to just the X as the pushout of the span. All right then, so the purpose is describing identity types of pushouts, because pushouts are pretty ubiquitous. You have your spheres, you have more generally you have your suspensions, you have your quotients. In general, anywhere that glowing spaces is the vibe, you reach out for pushouts. And we want to better understand their path spaces in general, because, for example, it allows us to make better connectivity and truncation estimates on these new spaces that we form. And what does it mean really to understand these path spaces? Well, formally, we fix one endpoint in the pushout, and then we want to give a type family over the pushout that's for some notion of reasonable to compute with. And we also give a proof that its fibers are equivalent to the path spaces or the identity types. We have this nice zigzag construction described by Wärn in 2023, which I consider pretty elegant and decided to formalize it. Now here we are 2 years later, and in the meantime, no other formalization popped up, but I finished mine recently, so now we have one, and that's why I'm standing here in front of you. As for the theoretical settings of the work, I formalized things in book hot, and I used the ActAnyMath library, which is a large library of mathematics. One should make an acronym out of that. And I plan to upstream these changes, which has some practical consequences. First of all, we only work with postulated pushouts, which means that we don't use cubical or any other means to get computational pushouts. which means that the triangles in the diagrams are not judgmental equalities. But elimination does not compute on constructors or pushouts. Then I also strive to make the code reusable and maintainable, which means proving in the most general way possible. And performance somewhat matters, since at the end of the day, it's supposed to be part of the library that other people use, and it's not nice if it ends up taking a long time to type check. And I also fix some conventions for the talk. So we fix this pushout, this span f and g, and its pushout ij and h on the type X that we want to study the identity types of. And there are also some other pushouts that pop up. And for those, I will use the identifiers inl and inner for the inclusion maps and glue for the square. And I also make good use of sequential colimits, which is another colimit just as a pushout is. In fact, it can be derived from pushouts in homotopy type theory. And the diagram is just a rightwards unbounded sequence of types and maps between them. And the cocoon is a sequence of maps iota and triangles kappa. And we can either draw it under the diagram or to the right of the diagram. Which now brings us to some description of the zigzag construction. So what we want, as I said, is construct this type family over the pushout, which is by definition a function from the pushout into the universe. So we can use a coupon with a vertex in the universe, and then that induces this type family. And this coupon consists of two type families, PA and PB, and homotopy. But by univalence, we can replace this homotopy with a family of equivalences. And so we give this new structure a pretty sounding name. We call it descent data. And it's this type of triples consisting of two type families over the two components of the pushout and a family of equivalences that in some sense says that those type families agree on overlaps in the pushout. Okay, so how do we construct those type families? We construct their fibers as sequential colimits. And we take this one base point in the A component as our base point that we want to reach out from with our path constructions. We intuitively want to say that the nth stage of this construction is the type of paths from this base point to some other point, such that we allow at most n crossings from one component to the other. And then when we take the colimit, we allow ourselves arbitrarily many such crossings. To start with, we see that there is really no way to get from A to B without any crossings. So BB at 0 is all just empty types. And to get from some point in A to some point in A without crossing is just taking the path space of A itself. And then we move on to the next stages, where we say that a path with at most n+1 crossings is either a path with at most n crossings, or it's a way, or it's a path with n+1 crossings into the other thing, and then we concatenate a path back to our destination. And these two operations allow us to interleave these connecting paths between the two components. And we consider these paths modular backtracking, to borrow a term from Wärn's note, and which says that whenever we go up and down or down and up immediately along the same path, then that's as if we did nothing. Like we portion those things away, which makes these fibers push out themselves. And this, then we just take the sequential colimit, and that gives us the two type families PA and PB. And how do we get the necessary family of equivalences? Well, we construct what's called a zigzag between those two sequential diagrams. Zigzags being the map down and up, and triangles, where the maps are just the right inclusions of the defining pushouts, and the triangles turn out to be the glue of those pushouts. And then this structure induces an equivalence in the colimit. And that completes the definition of this and data and gives us the type family I. So that's the zigzag construction. Now we want to prove that it actually satisfies the right universal property, or that it actually has this equivalence to identity type. How do we prove that? I chose to show that this type family is an identity system when it's pointed in a specific way. And I formalized that means that it suffices to show that the defining this and data is an identity system for a proper, or for a particular definition of identity systems of this and data. And that's pretty much a one-line restatement of the universal property of pushouts given by Krauss and von Raumer in their paper. And I just want to include this definition because I thought it's very slick. We say that this and data is, when it's pointed, is an identity system if for all dependent descent data over it, the evaluation map, which takes a section of the dependent descent data and evaluates it on the right component, has a section. It's not really necessary that we understand all of that. What we really need is to take a base point in this type family over the descent data and then give back a descent data equivalent of a dependent function. Okay, so that can't be that hard, right? First of all, we find the endpoint or the base point of the type family, right? So we can take just the inclusion of the reflexivity path in the colimit. And then we are given this quadruplet. We are given two type families over the fibers of the descent data, PA and PB, and we are giving this fiber-wise equivalence over the equivalence PS, and we are giving a base point in QA, and we are supposed to conjure this pair of dependent functions into the given type families, and this coherence datum, which is like a dependent square, where I say dependent because it's supposed to fill this shape, and the vertical maps are dependent functions, and the top map is a fiber-wise function, so it's not a regular rectangle, a regular square. It's what I would call a dependent square. How do we get there? Well, the two sections, or the two dependent maps, are out of the sequential colimits, so we use the induction principle of sequential colimits. So then it suffices to show a dependent function at every stage, and then some coherence. And we can define these two maps as together by just induction on the stages. It's a little tricky to define, it's a little technical, so I won't cover it in this talk, but you can read the associated pull request. And we construct the coherence square by proving some new functoriality lemmas for sequential colimits. And to be honest, this was really the hard part of the formalization. So I will just state the necessary steps that I took so that anyone who wants to formalize it in the future has this available. First, I showed that the homotopy of these diagrams on the left induces a homotopy of the induced dependent functions on the right, where I take the covert way of going through the identity types. So this isn't really computational, but I won't get into all that. Then I showed that taking the sequential colimits preserves composition of regular morphisms and dependent morphisms, right? So this composite on the left induces the composite on the right with an asterisk because there are some transports that I won't get into. Then we have a similar thing, which says that taking the colimit preserves composition of a regular morphism and a fibrous morphism. So the composite on the left induces the composite on the right. And this one actually goes through as stated, so that's nice. And gluing it all together, we get this thing that this theorem that says that dependent cubes induce a dependent square on the collimate. What does that mean? Is that if we start with a morphism of sequential collimates, of sequential diagrams, then it induces a map in the collimate. Then we get a function, the dependent type over the collimate and induce a dependent function into it. We do the same thing for the other dependent type. Then we get an equivalence over the map in the collimate, which in turn induces these functions over the diagrams. And then we say that if we fill those cubes, which again are dependent cubes, since the vertical functions are dependent and the top has a given transport, hidden transport somewhere, then if we fill this, then we successfully fill the square on the right, which is the objective, the hole we want to fill. And that's it. That's the steps that I took to fill the square. So I will move on to the concluding remarks. So the first thing that it's done, the formalization and finish, the construction is proven correct. Formalizing the construction itself wasn't really that difficult. It was pretty straightforward. But then proving and defining the sections of the proof was more difficult computation-wise. And there were some choices that actually influenced whether the rest of the proof would be difficult or not. And my experience with drawing diagrams was that it's useful to finding the right statements and convincing the formalizer, but not so much convincing the proof assistant, which is unfortunate. There is some future work, as always. We still want to have some applications formalized, because right now we just have the construction. Some results about sequential collimates are not proven in full generality, as I would like. And then I still need to work on optimizing the proof. You can read the times here. The thing is that currently the main file takes about a third of the time to type check as the rest of the library, which is nice. But at least this bottleneck is pretty localized in two symmetric definitions that I unfortunately didn't get to talk about, but you can talk to me about it after. And to finish off, I'd like to present some related work. First of all, Wärn released a second article, which presents the construction in an unstraightened version, which means that instead of working with type families who are function into the universe, it's a type and a function into the base type. There's also an independent formalization in ROC by Ben Connors and Tom Thornbjörnsson, but it's still unfinished. It's still missing this square that I struggled with. And then if you want to learn more about the technical background of the formalization, some more stuff about descent and the identity systems that I mentioned, then I invite you to check out my master's thesis. And with that, I'll thank you for your time and hand over back to the chair.
We have some time for questions. Yeah, Torsten?
Thank you. It seems to be a nice piece of work. Actually, it's related to the last talk. So, I mean, in cubical actor, you said you had push out as a axiom, as a assumption, right? In cubical actor, we can define it. Why not use cubical actor?
The same reason as in the previous slide. We are working in Agda Unima.
Fun?
We are working in Agda Unima, and
yeah, maybe that's a mistake, no? No, I mean, I don't understand why we have a type system which is well behaved, and everybody seems to avoid it. I mean, I'm aware that there are problems, but maybe they need to be addressed instead of bypassing them. I mean, it's not a criticism of you, obviously. It's just the general remark.
Yeah, the social background is that I started this work as my master's thesis, and Egbert was my supervisor. So
yeah.
So I would like to ask about the construction, because I think there's something that I don't quite understand about it.
Sure.
So let's say that we have a path that goes first in A and then goes into B and then up in A.
Yep.
But then the path in B happens to be in the image of S. So then it's supposed to be cancelled out somewhere, because then we could have just lifted it to a path that is completely in S and it should be done in one step. So where in the construction does this cancellation sort of happen?
That's the module of backtracking.
Okay, thanks. Could you go back to the zigzag slide?
This one?
Yeah. What is this notation with the bullets?
Oh, yes. So this is a more evocative name for the right inclusion of the defining pushouts, and so that's the map that here takes the path into the other component and concatenates this guy. Right. So you take here you take a path that happens between two endpoints at the top, and you go down and you concatenate this path that's given by S right into the its endpoint GS.
Okay, thanks.
Yeah.
More questions?
Yeah.
Maybe as a follow-up to Thorsten's question, I know it's not done cubical like that, but do you think it would have been significantly simpler if you had had computation rules for push-out eliminators and stuff like that?
I don't think the formalization itself would be hurt. I don't think if we translated the formalization now to cubical agda, then it would be much simpler. It might be simpler to come up with all those proofs in cubical agda because I would have smaller goals. And so I myself am very interested in whether an agda formalization would be easier, but I haven't investigated it, and I know very little about cubical agda, or I have very little experience with it, so I can't really tell.
Thank you.
Okay, I'll ask one question then. So you mentioned these transports at the end.
Yep.
Are these kind of like incurred because of you don't have these judgmental computationals for pushouts, or are there different kinds of transports?
I think those are different kinds, right? Because that's just what a dependent homotopy.
Okay, it's just because of the dependencies. Okay. And then my other question was going to be, so the second article that David Wärn wrote, was this useful at all in like guiding some of this development, or was it really the first version that was useful for you?
I mostly went off the first article, since the second article came out when I was already working on it, and I didn't really connect much the proofs from the second article with what was in the first article.
Yeah, it could be interesting, I think, because sometimes when these more categorical arguments are sometimes more lend themselves to formalization. Okay, any final questions? No? Then let's thank Wojtek again and let's have coffee, please.